Hello, I'm Barbara Liskov. I'm an institute professor at MIT. I've been here for a long time, and my research has been focused in the areas of software systems and programming languages. And today I'm going to answer some questions about the work that I've done. And here's the first question. How did you conceptualize data abstraction in the early days? Could you walk us through the technical thought process that led to its formulation? I started working in the area of the software crisis around 1970, and this was when people simply did not know how to build software systems that worked. And they were interested in the concept of modularity. How do you divide the program into separate sections, each of which can be reasoned about independently? I had already invented a kind of module that had more structure than other people had, in which there was a bunch of code with hidden state inside, and it provided a bunch of operations that the rest of the code could use to interact with it. And I was thinking, when I first came to MIT, about how to make that concept of modularity be more useful to people so that they could actually use it in their work. And at some point during my first few months at MIT, I suddenly saw that that notion of a module could be thought of as a data type. When I look back at the literature now, I see data types floating around in those papers, but I happened to have the good luck to see the connection. And this was a very important idea because data types are how we reason about the design of programs. What was your experience in developing different programming languages like Argus and CLUE? Programming language design and implementation is not so bad, but design is very difficult because what you're doing is you're inventing a user interface with very little constraints about what you're trying to do. I developed CLUE as a way of exploring the notion of data abstraction and making sure that it was a practical idea that could be used when people built their programs. And Argus later I developed when I started to work in distributed computing to see how notions of data abstraction and object-oriented programming could work there. What is your reaction to the success of the Python programming language today, given it was influenced by CLUE? It's great that Python is successful. It has a major problem from my perspective, which is that it does not provide for encapsulation. It doesn't make sure that code outside of a module is unable to access the internal information of the module. And this means that people can easily make mistakes that cause modularity not to work. What this really means is, since Python is mainly used in large part for teaching, is that this notion of encapsulation has to be carefully taught to the students so that they understand how to force themselves to do it themselves. Could you explain the technical nuances of the Liskov substitution principle? Perhaps you could discuss a complex scenario where adhering to or violating this principle has significant implications. What happened with the Liskov substitution principle was that I was asked in around 1986 to give a talk at OOPSLA, which is the main object-oriented programming conference. And this was going to be the second OOPSLA. And I decided at that point to look into what was going on with Smalltalk and its derivatives. I was already working at this point in distributed computing, and so I hadn't been paying much attention to this. And what I discovered was that Smalltalk and its derivatives used inheritance, where a class could build its implementation based on the details of the implementation of the superclass. But people were also interested in using this notion of class and subclass for a type hierarchy, where you could write code in terms of the supertype, and it would be okay if when you ran, you got objects of the subtype as arguments. And I discovered in reading the papers that people didn't understand what it meant for type hierarchy to work correctly. And an example of an error I found in these papers was that there was a paper that argued that stacks and queues were subtypes of one another. And this was clearly false, because if you wrote code expecting a stack with LIFO behavior, and instead you received a queue with FIFO behavior, it was very unlikely that your code would continue to work properly. And so this led me to come up with the Liskov substitution principle, which had to do with the semantics of the type and the supertype. And what it said briefly was that the subtype has to behave like the supertype when used in a context where the supertype is accepted. So it's a semantic definition. Later on with Jeanette Wing, we provided a formal definition of what this meant. Can you talk about some of the work that addressed the challenges of consistency and fault tolerance for information stored online? When I finished working on CLUE, and this was in the late 70s, I was looking around for what the next project was, and I didn't think I wanted to continue in programming languages per se, because I thought I had answered all the questions of interest in CLUE. At least I couldn't think of more questions of interest that I wanted to work on. And I happened to read a paper by Bob Kahn, one of the founders of the internet, in which he discussed his dream of distributed computing, where you had components of the program running on different nodes in a network and communicating over the network, except nobody knew how to build distributed programs at that point. And so I thought that was a wonderful research area. And so I started working in distributed computing. The first thing I did there was the Argus programming language, which was really like CLUE language, except now the objects could be residing at different nodes in the network. And while I was working on Argus, I was also thinking about other problems that were popping up in the distributed computing area. And one of the ones that was very compelling was the notion of a shared file system, where the file system existed online. It could be used by people all over the place. And I got interested in the question of what do you need in order to make that file system work properly? And this led me to work in replication. Replication is needed so that even if one of the nodes where the file system resides fails, the file system is still available to others. And also I had to think about how to make sure that the whole file system worked correctly in spite of concurrency and also failures of various sorts. So that's how I got into that area. Could you discuss the technical aspects of your thesis, A Program to Play Chess in Games, and its impact on the development of algorithms in modern computing? So I did my graduate work at Stanford, and I worked with John McCarthy, one of the fathers of AI. At that point was concentrating in AI, and my thesis about chess has to be understood in the context of the time. So at that time, computers were very small and very slow compared to what we have nowadays. And chess was a problem which was solved through search. So we were searching through trees of possible successor states. And because of the lack of power in the computer, we couldn't do very much search. And so we had to invent heuristics instead. And so my thesis had to do with how do you do in games and what kinds of heuristics should you use in order to make the program work in that case. And it was important for what was going on in chess at the time. I would say it has absolutely no impact on what has happened in the algorithm since then. The world has changed a lot since then. But it was of importance at the time. How do you think object-oriented programming has adapted to managing increasingly complex systems, particularly in the realm of distributed computing and cloud technology? Object-oriented programming is beautifully suited to distributed computing and cloud technologies because each object is a closed universe unto itself, and the rest of the system is not supposed to get inside and muck around with what's going on inside the object. And so if it's sitting remotely from you and you already have to communicate it with it by sending messages, this exactly fits what the rules are. When I was trying to figure out how to make modularity work, I used to envy the electrical engineers who had to design things out of circuits. Because with circuits, you have to communicate by means of wires, and you can't afford to have very many of them. And you have to think carefully about what's going on in the interface of a module and how to connect things in an efficient way. Whereas in software, all we have is this one huge memory space, and we can go anywhere and do anything. So there was nothing inherently possible that was coming from the environment to control what we could do. And so if you think about distributed systems, they're a lot like circuits. You know, you have these different computers in different places. They have to communicate over the network. So naturally, you're going to have to think carefully about how do they communicate and what the interfaces should be. And this fits exactly with what's going on in object-oriented programming. So it was a beautiful fit. And that's what went on when I designed the Argus programming language, where I took advantage of the fact that Now the objects were distributed, and so instead of making local procedure calls, they communicated with remote procedure calls instead. As we edge closer to the era of quantum computing, how do you foresee object-oriented programming principles being challenged or reinvented? I don't see them changing at all. Object-oriented programming has to do with the big structure of programs. It's how do we divide this program into pieces so that we can reason about the pieces independently. What's going to change is the code. And I have no idea how it's going to change because I haven't been working in the area of quantum computing. But I think we can expect that programs will look different. The kind of code we write probably will be different. And by the way, as we do all sorts of things with computers, we have to invent a whole bunch of stuff that's different from the object-oriented programming that's the structure of the program. We have to invent protocols. We have to figure out all sorts of interesting issues that certainly didn't exist in the days when object-oriented programming was invented. Teaching opt concepts can be difficult. What approaches or methodologies have you found most effective in imparting these complex ideas to students? Actually, I don't think I have found them complicated to express. One of the things I did at MIT starting in the late 70s was develop the second course in computing, where the idea was the students already knew how to write code, but what they didn't understand was how to build big programs. And so my course was the second course where they now learned how to do design and so forth. And it was all about how to design programs, how to find modules, how to invent abstractions. And I talked about these ideas both conceptually by explaining what the rules were and so forth, but also by giving them examples and working through designs with them and showing how the design developed and so on. And it all seemed to work out just fine. It's just that design is different from coding. And it did seem to me as I went on that for some students, it was very hard to get the notion of how to do design. It was a slightly different thought process. But maybe that's what people think is difficult. For some people, I think design is complicated and abstraction is complicated. But as far as the course as a whole was concerned, I still sometimes get emails from people telling me how much they enjoyed the course, how important it was for their future career, and so on. And I should say, by the way, that course was designed jointly with my colleague, John Guttag. We worked on the course together, and we taught both the concepts of data abstraction and so forth, but also how to write specifications, how to reason about correctness of code, and so forth. In the era of multi-core and parallel computing, how do you see object-oriented programming adapting or evolving? Are there inherent challenges in OOP models when applied to parallel computing architectures? Again, it isn't that object-oriented programming is going to change, or rather, it's not that modularity is going to change. Data abstraction is not going to change. It's the way you organize your program. In fact, it works really well in a parallel environment because if you are careful not to have the code outside a module be getting involved in how the module is synchronized, then and leave that up to the module itself, you can do really clever things and nevertheless have code that actually works correctly. You could have several operation calls working in parallel, and it doesn't make any problems because you actually know inside the module exactly what's going on. So it's very well suited for a multi-core environment. And in fact, I've done a lot of work in that area in the last few years. So again, it's just like the distributed system thing. It works really well in that environment. Professor Liskov, what advice do you have for future students and researchers? For a while at MIT, I was the provost for faculty equity, which meant I was on the top council at MIT. And one of the things I did when I was in that job was I used to go to the graduations, and I would meet what we call the red jackets, which are the people who are coming back for their 50th reunion. It's an MIT tradition that they wear red jackets. And I would talk to these people about what they did. And what I discovered was that although some of them were still doing, in some sense, exactly what they started with when they graduated from MIT, many of them are doing different things. And they have adapted their career to accommodate both what opportunities presented themselves and also what their interests were. And so my advice to students is that as you go forward, and actually as you're a student, you think carefully about what do I enjoy and what am I good at? And you allow that to guide you through your education, through your future career, and that way you'll be successful and you'll enjoy what you're doing. So I've enjoyed answering your questions today, and I hope you've enjoyed listening to me. And maybe sometime we'll have a chance to have another conversation in the future. Thank you.